Hello and welcome back. In this video series, we are now going to look at the closed loop transfer function. Previously, we defined what is a transfer function, and we already know what do we mean by the open loop and the closed loop system and how they are represented using a block diagram. And maybe now I can define what is a closed loop system. So a closed loop system is defined as system having feedback where a portion of the output signal is fed back to the input to reduce the error and improve the stability. So the important thing to identify in a closed loop system is that it has a feedback and the output signal is fed back to the input. In that case, it helps to reduce the error and improve the stability of the system. Now I will again draw the block diagram, and we all know from the block diagram we have the desired input, and we have the comparator, and we have the controller, and we have the plant, and we have the actual output. And this actual output will be fed back using a feedback path, and this is nothing but the feedback path to the comparator. So this path is now the feedback loop. Now by applying the S domain representation, we can say X of S to the comparator to the controller, let's say C of S, and the plant P of S, and we have the Y of S, and we can say F of S represent the feedback and to our system. And in this system, if we are to derive the transfer function, the transfer function is equals to Y of S over the X of S. And from the definition, it says the output signal will be fed back to the input. And remember that X of S is a signal, and the Y of S is also a signal. That means this signal is responsible to enable the controller to adjust the working of the plant. Previously in our summing diagram, we look at if we have A and B as an input to the comparator, the output is C, and now C will be equals to, if this is plus and plus, then the output C equals to A plus B. And if we have A as an input and B as an input to a system where we have plus and minus, now we should have C is equals to A minus the B. And this becomes important where the C is called the error signal. Error signal. And this is called the comparator. And this comparator is responsible for comparing the signal. If we have A and B as a signal input, then the output C will compare the value of A against the B. And it is important for you to identify the sign that is corresponding to the input signal to the comparator. And unlike the comparator that deals with the signal input and the output, we have the block diagram which represent the gain. For example, if we have B of S, and we have y of s, and we have x of s as an input to the system. In that case, we use a product rule to determine the response such that y of s is now equals to b of s dot x of s, and b of s is nothing but the gain or the transfer function of the system, and the x is the input signal transfer function. And I have mentioned the difference between the gain and the transfer function. The difference between the two, the gain can be seen as a time domain function, whereas a transfer function is seen as the frequency domain function. Remember, if we have the gain beta equals to 3, and this is a system, and if we apply positive 5 volts as an input, we now know that the output will be positive 15 volts, and this represents the gain of a system. And when we talk about the transfer function, we can have x of s, example b of s, and we have the y of s, where x of s, b of s, and y of all of them are in the transfer function format. So it is mostly in the frequency domain, and this gain can be in the time domain. So I think all of this can help you to understand the difference between the gain and the transfer function and the summing operation of a system. So we will now look at how do we derive a transfer function from a control system closed loop system. And now we can draw x of s as an input to a comparator, and we can have e of s and c of s, p of s, and y of s. Then we can have f of s as the feedback, and this will become the input. And it is very important that we identify this one as plus and plus. And when we have plus and plus, this system is known as a positive feedback closed loop control system. And also we can have R of S, which is the product of the response and the feedback. It is very important for us to know that the X of S, the E of S, the Y of S, and the R of S, they represent the signal. And the C of S, the P of S, and the S of S, they all represent the parameter of a system. So this parameter can be a variables, and the signal can also be seen as a variables. So it is important for you to differentiate between the signal and the parameters of a system. So from here, we can now look at the signal such that we can firstly look at E of S. So we all know that E of S is equals to X of S plus R of S. And it is a summing operation where we seen previously such that if A and B is an input to the system, the output will be C. And this output C is equivalent to A plus B. So that's how we derive the S domain representation of the signal. And also we can look at the signal. R of S is equals to f of s times y of s. So this derivation is important in order for you to simplify how to obtain a transfer function. So from there we can look at the response of the system. So the response is y of s. So y of s is now equivalent to the e of s, which is the error signal, multiplied by the c of s and the p of s. That means the error signal is the representation of the error signal in the s domain, and c of s is the representation of the controller in the s domain. And now we can further simplify by substituting e of s into this equation. So we have x of s plus the r of s. We can now substitute this r of s into this equation such that f of s dot y of s, and we can multiply all of these with c of s dot p of s. So this is our response of the system. So if we now want to multiply the system which is outside the bracket with the one inside the bracket, we can simply say y of s is equals to x of s dot c of s dot p of s plus this multiply with f of s dot y of s dot c of s dot p of s. The important thing why we want to simplify the response is that if we want to obtain the transfer function, we need the x of s and the y of s. So this becomes very important because in this equation initially doesn't contain the parameter y of s and x of s separately. So we have to perform the simplification method such that we simplify the entire system so that we can extract the x of s and the y of s. So we can see we have two y of s and one x of s. So we can see that if we now want to extract only y of s and x of s, we will bring this equation to the other side such that it will becomes minus f of s dot y of s dot c of s dot p of s is now equivalent to x of s dot c of s dot p of s. So now we can bring the y of s outside. We now have y of s is equivalent to 1 minus f of s dot c of s dot p of s, and is equivalent to x of s dot c of s dot p of s. So we can divide this equation so we can have the response, which is y of s is equals to x of s dot c of s dot p of s divided by 1 minus f of s dot c of s dot p of s. And now we can bring this x to the other side. We now should have y of s over x of s is equivalent to c of s dot p of s over 1 minus f of s dot c of s dot p of s. So now this one is nothing but our transfer function. And we said that in a mathematical modeling, we normally use a differential equation and the transfer function. When we are using the transfer function, this is how we derive a transfer function from a closed loop positive feedback system. And then from this transfer function, we can now perform analysis to analyze this system. And remember, this is nothing but a positive feedback transfer function. And we will also do comparison with a negative feedback, because a negative feedback is mostly used in control system design. And if we now have positive as an input and minus for the feedback, we now have what is called the negative feedback closed loop control system. So we will derive the transfer function of the negative feedback, and we can compare it with the positive feedback transfer function that we derive. So similar to what we have discussed earlier, now if we have the error signal E of S is equals to X of S, now we should have minus R of S, and this represent the error signal. And we can have the R of S, which is F of S dot Y of S, and we can say that this is nothing but the feedback signal. And remember that X of S is the input signal and Y of S is the output signal. The response of this negative feedback system can be seen as Y of S is equivalent to E of S dot C of S dot P of S. So we can now substitute this equation such that Y of S is equals to X of S minus R of S is now equals to F of S dot the Y of S. And we can have the C of S dot P of S. So when we perform the multiplication with respect to whatever that is inside the bracket and outside the bracket, we can have Y of S is equals to X of S dot C of S dot P of S minus F of S dot Y of S dot C of S and the P of S. So since we have the signal such as the output and the input, we can now group the output and input separately. So we can break this equation to the other side. We have Y of S. Now this minus will become plus F of S dot Y of S dot C of S dot P of S, which is now equivalent to X of S dot C of S dot P of S. So we can bring the Y outside the bracket, so we have only one variable, Y of S. So it can be 1 plus the F of S dot the C of S dot the P of S. Now it is equals to X of S dot the C of S dot the P of S. So we want the X of S and Y of S to be on its own, so they represent the transfer function. So we have Y of S divide, we bring X of S to the other side, and we now have the C of S dot P of S, and we bring this portion to the other side. That means it is now divided such that 1 plus F of S dot the C of S dot the P of S. So now this becomes our transfer function, and it is not an ordinary transfer function, but we can say negative feedback transfer function. So you can differentiate between the two, both positive and negative. They have the same type of S-domain representation. The only thing is the sign. In a negative feedback system, you have positive, and For the positive feedback system, you have a minus. So we discuss in this video the negative feedback and the positive feedback transfer function derivation from a block diagram representation of a closed loop system. And we can also derive another feedback system known as a unity feedback. So what is a unity feedback? If you like our video, you can kindly subscribe to support our channel and also share this video with your friends so they can be able to learn what is a closed loop transfer function and how we can derive the transfer function equation to help us analyze a dynamic closed loop system. So a unity feedback is a closed loop control system having input, controller, and the plant, and the output is fed back to the input. However, it is a unity feedback because it has a value 1. So if we are explaining in a time domain representation, that means a unity feedback will have a gain which is corresponding to 1. So if we are to represent this one in terms of the S domain, we can now represent X of S to the comparator, to the controller, which is C of S, and we can have P of S, and the output is Y of S, and we have the output connected to the input. So it has a unity feedback having a value of 1. So we are now trying to derive the transfer function of this unity feedback closed loop control system. And we can apply the same method such that this will become E of S, and because this is unity, we can say the unity is equals to the output Y of S. So we can say E of S is equals to X of S, and if we have plus and minus, we can say minus Y of S. Simple as that. And if we have both positive, we can have E of S is equals to X of S plus Y of S. So you can only change the sign with respect to the error signal. And now because it is unity, that means the input to the controller is nothing but simply the Y of S. So we can now determine the response of the system such that the Y of S, which is this one is the response, is now equals to P of S dot C of S dot the E of S. So we can just substitute this E of S into this equation. We have Y of S is equals to P of S dot C of S dot the E of S is equals to X of S minus the Y of S. So we can have Y of S is equals to multiply anything outside the bracket with the one inside the bracket. We have P of S dot C of S dot X of S, and minus we have the P of S dot C of S dot Y of S. So we bring this to the other side. We now have Y of S plus P of S dot C of S dot Y of S is now equals to P of S dot C of S dot the X of S. And we can bring Y of S outside, and it is now equals to 1 plus P of S dot C of S, and which is equals to P of S dot C of S dot X of S. To derive the transfer function, we only need the X of S and the Y of S. So we should have Y of S over, we bring this to the other side, becomes X of S, and we now have P of S dot C of S divided by, we bring this to the other side, it becomes 1 plus P of S dot C of S. So this is now our unity feedback transfer function. So like what we have seen previously, because this now is nothing but a negative feedback, so we have a plus. And for a positive feedback, what should we have? The transfer function should be equals to P of S dot C of S over 1 minus P of S dot C of S. So this can represent our positive unity feedback system. So you can try this to prove yourself if you can get this, which represent the unity feedback. And this is how they derive the transfer function for a unity feedback closed loop control system. We will also look at some simplified method in which if we have more system added to a closed loop, and how can we simplify to get the result. The important thing is that they will always attain a form of a transfer function such that y of s over the x of s, and from there it can be easily solved using a Laplace transform method when we include the signal itself. But for summary, you can see that for a negative feedback control system, we have y of s over x of s, which is equals to p of s dot c of s over 1 plus p of s dot c of s. And for the positive, we have y of s on x of s, which is equals to p of s dot c of s over 1 minus p of s dot c of s. And this represent the unity feedback closed loop control system. And we have seen that for a negative closed loop control system, we have y of s over x of s, which is equals to p of s dot c of s over 1 plus p of s dot c of s dot df of s. And for the positive closed loop, we should have y of s on x of s, which is equals to p of s dot c of s over 1 minus p of s dot c of s dot f of s. So in any order, if you solve, you should be able to have this form. So this is nothing but a standard form. No matter how many initial system that is integrated into the system, you should always return back to the standard form. And by understanding and knowing the standard form, it is mostly easy for you to calculate the system equation. And from there, you can be able to solve the transfer function corresponding to each of these equations.